This section of our lessons on introductory algebra is about translating between words and symbols. One of the standard mathematical practices is called attending to precision. And the reason this is important is because we need to be able to, when communicating mathematically, avoid ambiguity and confusion. And that seems pretty straightforward. Like, of course, we just have certain words for certain things, and as long as we use those words, everything will be fine. Well, that's actually not necessarily the case, because the order in which we use those words can really have a big impact on how we interpret them. There's a problem here, this expression, 8 divided by 2 times the sum of 2 plus 2, right? And maybe that's one way you would read that. This is what's known as a viral math problem, okay? And it's called a viral math problem because somewhere along the line it gets posted to Twitter or Facebook, and all of your aunts and all of your uncles and all of your grandparents and all of the so-called math experts in the world will start commenting on this, and they'll go back and forth arguing about whose answer is right, because the way this is written, the way that it's shown here, can be interpreted a little bit differently, and depending on how you remember something called the order of operations, which is something you learn in elementary school, and depending also on how your teacher taught it to you, you could very well get this wrong. There is totally a correct answer to this. The correct answer to this is 16, and the reason for that, just to be clear, is that this is the order of operations right here. This is the mnemonic we use. Please excuse my dear Aunt Sally. So parentheses first. 2 plus 2 is 4. So if we rewrite what we have now, 8 divided by 2 times 4, well, this parentheses right here, these is no longer the p part of the order of operations. This is simply just 2 times 4. So we don't have any exponents, and all that's left over is multiplication and division. And we just do multiplication and division left to right. So 8 divided by 2, that's 4, times 4 is 16. That's it. Now, it's forgivable that you would get confused on this, especially if you didn't see this expression written and all that was being said was somebody telling you what it says. So if somebody said 8 divided by 2 times 2 plus 2, that literally says it's 8 divided by 2 times 2 plus 2. Like, that's what it says. And yet, if I just heard that and I didn't see this expression, I might write that as like 8 divided by 2 times 2 plus 2. Well, that's not the same thing. And then what about 8 divided by the product? 8 divided by the product of 2 times the sum of 2. Okay, 8 divided by the product of 2 times 2, the sum of 2 plus 2. That's not the same thing. And even this one, 8 divided by 2 times the sum of 2 plus 2. 8 divided by 2 times the sum of 2 plus 2? Well, that is right, but the way I interpreted it there, but couldn't I have also interpreted that as the same way as before? 8 divided by 2 times the sum of 2 plus 2? Like, how do you know, right? And so you would have to be extra specific here and say it's something like 8, the quotient of 8 divided by 2 times the sum, times 2 times the sum of 2 plus 2. Is that right? 8, no, sorry, that's wrong. 8, I did that wrong. 8 divided by 2 times the sum of 2 plus 2, right? The quotient of 8 divided by 2 times the sum of 2 plus 2. That's really the only way to do this here. So, and get it 100% right every time. And that's not necessarily the first thing you think when you read this, but being able to communicate that specifically that way is important. Here's a bit more simple, a couple more simpler examples, right? If 5 times a number, well, what we need to do is recognize that a number here is unknown. So we can use a variable for this, or just a letter to represent something we don't know. So a letter we can always use is like n. N could be a number, x could be a number. It doesn't really matter. But 5 times a number would be like 5 times n. That's it. 6 less than 27 times half of a number? Well, to write this accurately, we kind of have to start back here at half of a number. So like n divided by 2, that's half of n, a number. 27 times that would be 27 times n divided by 2, and we want 6 less than that, so minus 6. So that might be a way that we can represent that. We could have also written that in some other ways that would be equally accurate, like 27x divided by 2 minus 6, same thing. Okay, x sub 1 is 216 more than x sub 2. What is x sub 1? That means sub is as a subscript. So maybe it looks like this. X sub 1 is, look, is an equal sign, is 216 more than x sub 2, right? So the value of x sub 1 is 216 more than the value of x sub 2. So let's combine these ideas here into this problem. This is an example of a distinct problem, and we can kind of write down what it says in this problem. So Mr. Gribble can climb a staircase in 10 seconds. Mr. Ulrich can climb a staircase in 15 seconds. If they start climbing a staircase at the same time and you combine their progress after 1 second, how much of the staircase will they have climbed? The first thing we need to identify is that if I can climb a staircase in 10 seconds, in 1 second I would climb 1/10 of a staircase. If I added 10 1/10ths, I'd have climbed 1 staircase. So this is how much I can climb in a second. And Mr. Ulrich can climb 1/15 of a staircase in a second. And if I add these two together, I will get some amount. Maybe let's call it x. How much of it? I don't know how much. X much of it? So let's calculate what this is. We have to this is simply a matter of adding fractions, and we can do that. The common denominator between 10 and 15 is 30, so we just go, we would say 3 times 3 divided by 3 here, times 2 divided by 2 here. So we would end up with 3/30ths plus 2/30ths, which is 5/30ths, which reduces, because we know 5 is prime, and then 5 times 6, that's how you factor 30. So that would go like that, and we would have 1/6. So together, after 1 second, we will have already climbed 1/6 of the height of the staircase. And so that's a way that we can just kind of take what is written out in a problem, translate it accurately into numbers and symbols, and then go ahead and use those numbers and symbols as abstractions to solve for a problem.